Friends, very good morning to everyone. We dealt with two drugs, meconazole and metronidazole, the imidazole containing drugs. Today's subject of discussion is the synthesis of ketoconazole. It is also an imidazole containing drug. This is the structure of ketoconazole. This is used in the treatment of fungal infections and yeast infections of skin. It is used to treat this seborrheic dermatitis, which is a condition in which it causes dryness, itchiness, and flakiness to the skin. Though it is a very good antifungal agent, it do not have any effect on bacteria or viral infection. Here it has the nucleus and this is the side chain. First we have to prepare the nucleus and then the side chain and combine the side chain with the nucleus. This is the strategy followed for the preparation of ketoconazole. We take this part, dichlorophenyl group is there with CO. That's why I'll take dichlorophenyl acetophenone. And here we have CHO, CHO, CH2O. I have three carbons attached to three oxygen. That's why I want to take 3 carbon 3 oxygen donor. And that should react with dichloroacetophenone. I'll take glycerol and dichloroacetophenone, to be precise 2,4 dichloroacetophenone, and treat with glycerol, and the OH in the glycerol has lone pair of electrons as it is in sp3 hybrid form. This is electron rich and carbonyl carbon is electron deficient. As unlike poles attract each other, it attacks on the carbonyl carbon and it has to maintain its tetravalency. That's a pi electrons moves onto the oxygen and it converts into OH. The OH which is formed has lone pair of electrons and this carbon is positive center. It OH lone pair of electrons attack on the carbon and OH gets kicked off and it loses H plus and OH minus loses water molecule and cyclization takes place to give the ring system. The CH2OH which is free, I am blocking with treating by benzyl bromide. This is the positive center due to the electronegativity of the bromine. OH lone pair of electrons are there. That's why it becomes electron rich and this is donated to the positive center and bromide gets kicked off. H plus and Br minus, they combine together to lose as hydrogen bromide and I will get OH blocked by benzyl group. Here there is CH3 group. This CH3 I will treat with bromine. Bromination of the methyl group takes place and I will get corresponding bromomethyl derivative. I have synthesized the nucleus to which I should add imidazole. I will take imidazole. Nitrogen is in sp3 hybrid form, that's why it has lone pair of electrons and this carbon is the electrophilic center as It is having an electronegative group bromine attached to this carbon. This is electron rich nitrogen. It donates its electrons to the electrophilic center and it has to maintain the valency, and hence bromine gets kicked off. H plus and Br minus, they combine together to lose as HBr, and I have got the imidazole ring attached to the methylene group. I have synthesized the nucleus of the ketoconazole. Now I have to prepare this side chain. How will I prepare this side chain? Let us look into it. N-anisile piperazine I will take and treat with acetyl chloride. The carbonyl carbon is an electrophilic center as it is flanked between the two electron withdrawing groups oxygen and chlorine. Nitrogen has lone pair of electrons. It donates to those electrons to the electrophilic center, and chlorine is an easy leaving group and it kicks off as chloride ion. Chloride ion and H plus ions combine together to lose as HCl, and I'll get corresponding N-anisile, N-acyl piperazine. This, if I hydrolyze by using hydrogen bromide, I'll get corresponding N phenol N acyl piperazine. The side chain which I have constructed, I have to treat with the nucleus and combine. Then I can get the ketoconazole. I have taken the nucleus in which the OH is protected by benzyl. I'll remove it by hydrolyzing with sodium hydroxide. OH minus attack on the electrophilic center, and the bond breakage occurs between oxygen and the carbon, and the O minus, it combines with H plus and it gives rise to corresponding OH. Yes, attacks on methyl sulfonyl chloride. Why I have to treat with methyl sulfonyl chloride? OH is a difficultly leaving group. It is not an easy leaving group. I have to make it easy leaving group. If I attach this side chain to this CH2, then I will get ketoconazole. And OH, as it is not an easy leaving group, I increase the bulkiness of the OH by treating with methyl sulfonyl chloride so that it becomes easy leaving group. Sulfur is flanked by 3 electron withdrawing groups, making this electron deficient center. OH has lone pair of electrons, which is electron rich. It donates to the sulfur and it has to maintain its valency. That's why chloride gets kicked off. H plus and Cl minus loses as HCl, and the bond between the oxygen and sulfur forms to give corresponding methyl sulfonyl derivative. This methyl sulfonyl derivative is treated with the side chain. OH has lone pair of electrons. Sulfur here is electronegative. OH is O is electronegative. They are pulling, they are making this carbon electrophilic center. The electron rich oxygen donates its electrons to electrophilic center, and the methyl sulfonyl group gets kicked off and methyl sulfonic acid, and I get ketoconazole. This is the synthesis of ketoconazole. Another derivative is there which has structural similarity to ketoconazole, that is terconazole. Terconazole is structurally similar to ketoconazole. In ketoconazole, you have seen that there was imidazole ring system. Instead of that, that imidazole is replaced by triazole. Here it was N-acyl group. Here it is replaced by isopropyl group. Terconazole is the first triazole based antifungal agent discovered. It was developed by Janssen in the year 1983. It has been used in the treatment of vaginal infections. It inhibits cytochrome P450 14 alpha demethylase, and thus it decreases the permeability of fungal cells and disrupts, hence act as antifungal agent. The nucleus is similar except for that in ketoconazole it had imidazole, here it is having triazole. That's the same strategy what we followed for the preparation of the nucleophile of ketoconazole can be followed here. What we took? We took dichloroacetophenone, to be precise 2,4 dichloroacetophenone treated with glycerol, and we got the OH reacting with carbonyl to give the carbon oxygen bond, and carbonyl group gets converted into OH. The lone pair of electrons on the OH attacks on the carbon, and OH gets kicked off and loses as water molecule, and cyclization takes place, which reacts with benzyl bromide to give rise to O-benzyl derivative, which is treated with bromine. The methyl group gets converted to bromomethyl. This bromomethyl group, which is here, bromine is replaced by treating with triazole. There we treated with imidazole, here we treat with triazole. This has lone pair of electrons. The CH2Br, CH2 is the electrophilic center. Because of the electronegativity of the bromine, it attacks on the lone pair of electrons, attacks on the positive center, and bromide ion gets kicked off. Bromide ion and H plus ion combines together to lose us HBr, and I prepared the triazole containing nuclei. This I'll treat with the side chain. I have to prepare this side chain. Let us look into the preparation of this side chain. I'll take N-anisile piperazine as we have taken in case of ketoconazole. There we treated with acetyl chloride, but here we treat with acetone because we should get isopropyl group attached to NH. NH has lone pair of electrons. Carbonyl carbon is electrophilic center. The lone pair of electrons is attacked on the electrophilic center. It has to maintain its tetravalency for its stability. Pi electrons kicks off onto oxygen and it becomes OH. I have got NH over here. This is the positive center. To satisfy the positive, the electrons moves and H plus goes away. This CHOH, I am reducing it by treating with hydrogen and palladium, a reducing agent. I will get corresponding from alcohol to alkyl. I got isopropyl group attached to the nitrogen. N-isopropyl N-anisile piperazine. I will treat this N-anisile N-isopropyl piperazine with hydrogen bromide. This hydrolyzes the methoxy group and I'll get corresponding OH group. I got N-isopropyl N-phenol piperazine. I combine this N-isopropyl N-phenyl piperazine with the nucleus. The nucleus in which I have protected the OH group, I'll hydrolyze it by using a base like sodium hydroxide and I'll get corresponding alcoholic group which has the lone pair of electrons, reacts with methyl sulfonyl chloride, loses HCl and gives the methyl sulfonyloxy derivative. We have done this to make OH a bulkier and easy leaving group. I'll treat this with N-isopropyl N-phenol piperazine. The OH lone pair of electrons attack on the electrophilic carbon and it kicks off the methyl sulfonyl group as methyl sulfonic acid. And I have got terconazole. Terconazole is another antifungal agent, a first triazole derivative which is used as antifungal agent. This is all about the drugs containing the imidazole ring system and the triazole ring system. Next class we will deal with other syntheses of heterocyclic compounds. Till then, have a nice day. Thank you.